Hello, and welcome to our talk on defining the next 50 Reefs Portfolio. I'm Tim McClanahan, the Senior Scientist for the Wildlife Conservation Society, and I'll be introducing you to this topic, for which we'll have discussions later next week. I think we can agree that climate change impacts on coral reefs are complex. We do not know what will happen in the future. The future is going to be stressful and challenging for coral reefs. And because of this complexity, a portfolio approach is likely to be the best option. What will go into this portfolio, however, is not clear. How we can build it, how we can use the best available science, these are the important aspects of this next stage of conservation that we need to consider. Consequently, here I'm going to review the existing science of large-scale impacts on coral reefs. I'm going to summarize the large-scale climate sanctuary literature, the geography and maps. I'm going to compare some of the alternative models of climate stress in the Indian Ocean, and this will help outline the key questions and research needs to create this ambitious 50 reefs approach. Many of you will remember back in 2010 and 11, we produced a paper on prioritizing key resilience indicators. We came together in order to improve the existing knowledge on resilience and develop a consensus on both what was well known and what was not known, in order that we could develop a weighting system to weight various environmental factors in their ability to either create resilience or not. We found that this evidence-weighted framework improved the existing unweighted methods at the time and helped to develop more science-based, evidence-based approaches to identifying key sites. The hope here is that we can undertake a very similar exercise in which we are examining sanctuaries, climate refugia or sanctuaries, in order that we can develop a similar consensus view on where these next 50 reef sanctuaries should be located. In order to facilitate this process, it's important to understand the system view of resilience and climate change impacts on both natural systems and human systems. It's also important to share some similar definitions. The way I view sanctuaries is that they're something that can be modeled. They can be statistically and mathematically modeled, and the first step in modeling is often having clear definitions. In many cases, ecologists have borrowed much of this language from the better developed social sciences associated with disaster and risk assessment. In many cases, we also mix terminology, and this often can result in some sorts of confusion. So in many cases, I try and use a social ecological terminology whenever possible. It tends to have been given more thought over time, and they seem to share more clear definitions. If we're going to understand sanctuaries, we have to understand the inverse, or the vulnerability of corals. In many cases, it's the vulnerability that we're evaluating, and those areas that are not vulnerable, in fact, are those areas that are most likely to be sanctuaries. Remember, in terms of the climate sanctuary literature, there are three types of sanctuaries. There's avoidance sanctuaries, resistance sanctuaries, and recovery sanctuaries. Each of those has its own elements of factors that create vulnerability in those different systems. The exposure is largely the physical aspects of the physical chemical aspects of the environment: light, heat, water movements. And this is one of the more powerful ways to identify sanctuaries, but it is only one of three possible types of sanctuaries. Another is a resistance, which is the vulnerability is measured as sensitivity. This is essentially a biological metric. It has to do with the coral as a holobiont, the community of organisms associated with the coral, and in many ways the evolutionary history that's produced that particular holobiont and its ability to adapt or resist environmental disturbances or exposure. And finally, there's the adaptive capacity or the recovery aspect of a sanctuary. And this is largely driven by ecological considerations. These are the community change aspects of competition, predation, and parasitism. All of these interact and create what is a sanctuary type, and in many cases, just like the resistance versus recovery debate and whether they were different or not, how much they overlapped, we're going to enter into a similar type of debate as to avoidance, resistance, and recovery. To what extent are they similar? Do they overlap at all? Are they completely different sorts of aspects of sanctuary? And practically, how should we focus our work on those three types of sanctuaries? In order to do that, you have to understand the variables involved here. And that's a complex activity and one that we're trying to solve here. A healthy approach to building a portfolio is to examine what other fields of science, and in this case finance, have contributed to portfolio theory, what they've learned from it. And the key aspects of building a portfolio are essentially analyzing risk and generally avoiding it, and in some cases embracing risk when there's the possibility of high returns. So in many cases it's the balance between risk and reward that is often being considered in finances. And in many cases we have a very similar situation for coral reefs, where we have particular risks associated with either poor understanding of what creates disasters and poor returns in coral reefs, and understanding what the possible returns are in terms of maintaining a healthy system, a biodiverse system. This is a two-dimensional case here, but we need to think in other dimensions. I've mentioned that we have three axes. We have an exposure axis, a resistance axis, and a recovery axis. And therefore, you can think of this as a multidimensional problem where each of those axes has its own risk and its own reward. Many of those numbers are not well understood, but we know they each contribute to sanctuaries in some way. And it's possible that by diversifying the axes involved in our portfolio, we actually reduce the risk. Because if we over-rely on any one of these axes and our estimates are off, then the ability to reap the rewards is considerably compromised. So the issue for me is, how then might we balance these three axes in order that we reduce our risk and maximize returns? That is, if one particular aspect of sanctuary, say recovery, has very good returns, we would like it to be included in this final portfolio of reefs. The current, as I'll talk about later, the current exposure axis is our dominant axis at the moment. And part of what I'm proposing here is to consider a more balanced portfolio where resistance and recovery are part of the overall portfolio for coral reefs. So what I'm going to present to start out this conversation is a review of the literature. I call this my COVID-19 hermitage calling. I was caught between COVID in Kenya and COVID in the United States. and mostly hiding out in a remote area, small town. And one of the things I decided to do to start up this project was to reread the literature. I've been following the literature pretty carefully for a while, but as you'll see later, there's been an acceleration in the literature in the last 4 or 5 years. And I felt that maybe this was the time for somebody to reread this literature and think about what it means for specific topics such as sanctuaries. So you will be the benefit of me reading many papers. I think in the end I selected a smaller group of papers to analyze, 114 what I call empirical evidence papers and around 34 sanctuary papers. So what I'm going to do is briefly go through this compilation of this information that I made on these papers, and sort of develop a kind of a glossy overview and not get into the details at the moment. Many of you will probably be fairly familiar with the older literature and maybe some of the newer literature. But my effort here is to bring us all to one location in terms of understanding the current literature. In these cases, all of these papers begin in 1994. I see that as sort of the first, exposure papers, essentially. And then I stopped the review in March 2021, which is when COVID broke out. And then I sat down and started to compile this literature and look at it. What I'm going to look at is not the entire coral bleaching literature, but mostly the field data, the field empirical studies, the multiple site studies, where some measure of bleaching and or mortality were measured over time and between sites. So I'm taking advantage of the larger N studies, if you like. In the beginning, there's a few that are not particularly large, but they generally tend to increase over time. So we're generally going to get an overview of people comparing environmental factors over time, specifically over thermal stress periods, and then how corals responded either as bleaching and mortality. In order to simplify the literature a little bit and to get our heads back into the history of this literature, I've broken up the literature into 4 time periods, which are often associated with some of the key periods of thought and theory advancement in this period. And before 1998, when we had our global bleaching event, a lot of the questions arising from the 83 and the 88 event were, what is bleaching? Why is it caused? What are the various variables involved? And probably just as importantly was the idea that the symbiont relationship with corals could potentially be an adaptive mechanism, and that there's more of a landscape of algal symbionts, and that they may be switching or changing over time, and that's led to this debate about stability of this relationship versus fragility, and there's a deep literature now on that in the more experimental work that I won't go into, but this is sort of the roots of it go back here, and more follow the empirical field study work, which I see as developing in 1994 with the first satellite measurements estimating water temperature, and then the correspondence or coincidence with hot spots. The 2 early papers influential there are Garros and Hayes, and Hugh, Goldberg, and Salvant, where they both embrace the idea that there's a 1 degree centigrade threshold before corals bleach, and that leads then into the models that Ove develops, that I consider the first sanctuary models, because he acknowledges that there are differences between sites in terms of when regular bleaching will occur, and in many cases those identify potential sanctuaries, areas where there is some additional time before bleaching becomes a serious enough problem that many reefs will functionally die. And in many cases, Donner scales that up to a larger scale using the satellite data, and gives a more large-scale estimates that based on the more limited and patchy evidence that was occurred back in 1999. Starting sort of in the middle of that period from 2004 to 2020, I see spatial modeling and testing of theories and more evaluation of empirical data as being important. We get examples in the Great Barrier Reef where they were measuring water temperatures and looking at correlates with bleaching. In my case, using shipboard measurements in East Africa and its correlations with bleaching and mortality. Looking at some of the more atypical measurements, not just degree heating weeks, but measures of variance around temperature, skewness, kurtosis, things that I'll discuss a little bit more later. And then formalizing some of those relationships into models based on empirical data that estimate bleaching impacts based on multiple variables. The MINA model is based on 9 variables. It is satellite-based, but it's more inclusive of currents and light and water quality issues. And in many cases, efforts to more tie these theories to empirical data. I think Mark Eakin's paper in 2010 does that in terms of trying to find a relationship between thermal stress and bleaching and mortality for the Caribbean. And in many cases, Donner does a more critical evaluation of temperature metrics and finds that the +1 degree centigrade is in many cases due to the fact that that's sort of the 95% confidence interval. Outside that interval is for many of the locations of the world, but not all of them, which is an important finding. More recently, there's sort of this more application to sanctuaries and a bit more testing and modifying of global or very large-scale data. And I see the Bayard paper I'll talk about more later, where sanctuaries are formalized. The Sully paper, where the reef check data is evaluated for global scale bleaching events and the many factors that are influential. And I think of my nature climate change is looking at many variables, 20 variables in that case, and bleaching and finding it's quite complex, and the interaction between variables is often the strongest models or predictors of coral bleaching. And then the recent paper in Global Ecology and Biogeography, where we show that region is actually a very important part of the sensitivity of corals, that sensitivity is not uniform but seems to be geographically variable and located in various places that may have something to do with the historical variability in these locations. So in terms of the studies, I'll break it down into evidence studies, studies to find what evidence there is for this response in the field, not laboratory, and then sanctuary models where people have used various techniques, both threshold and or variability type models to estimate and locate where these potential sanctuaries might be, and also the type of sanctuaries based on the particular type of environment. In this case, one with high light and one with low light conditions. If you look at the historical timeline on these evidence studies, you'll see that some of the old favorites, the threshold models, have been actively being pursued for some time. There's an acceleration of them in the last few years. And that many of these other additional modifying variables tend to be added more recently in the last 4 or 5 years. That gives you an idea of sort of the initial conditions and sort of the modifications that are going on now in terms of the scientific literature. If you look at these variables, which identify 58 variables with some pooling of similar variables, you'll find that on average people study about 5.5 variables with a lot of variation around that, with the maximum of 20 and the minimum of 1. You'll see that the degree heating weeks or the threshold type models are actually among done in more than half, or 64% of the studies, whereas some of the other variables are much less. Usually people look at reef site as a variable in their models, but less frequently at geography and some of the more maybe unusual temperature metrics. And even light is really not that well studied in many of these cases, despite it being often an important part of the threshold model. But it's not, I guess light is seen to be as more stable over time into the future, and therefore not as big a concern as rates of rise, thresholds, and subsequent consequences. Modifying variables as well. Generally, not a lot of modifying variables. When they tend to be something to do with a deviation from mean temperature, oscillations, coefficients of variation. In many cases, those are found to be strong, and some of the other temperature metrics of shape distributions of SSTs are not that common in many of these studies, but often in many cases they find them to be important variables, as I'll discuss later. As I was reading this literature, it became clear that there were two types of modeling going on in terms of evaluating environmental stresses. That was the threshold model that we've discussed, which generally had a smaller number of variables. People were focused on temperature, rates of rise, the threshold concept. In some cases, light and storms were included, but in general, these evaluations were typically based on the environmental stress of temperature and not a broader set of stresses. The variability model looks at more types of environmental variables and potential stresses for corals. They typically include habitat, taxa, currents, geographic location, and many other variables. Sometimes SST is included, but there are many ways of evaluating SST, that is, measurements like kurtosis and skewness or coefficients of variation, etc. So as a result, the PCA sort of confirmed my estimate of the types of models that are being used in these two different systems. If we examine the papers and citations over time, you'll see that there's quite a large increase in papers after 2015, possibly an exponential increase. Another interesting pattern is that the variability models, in terms of numbers of papers, are generally outstripping the threshold model papers now, although they're fairly similar in terms of the sanctuary papers. If we look at citations, cumulative citations, that tends to be saturating over time, with the threshold models getting an earlier start, but mostly tracking one another in recent time. Just to talk about, bring it down to a few key papers of sanctuary papers. These are the ones that I consider sort of the most influential, which, as I already mentioned, Ove's 1990 paper has gotten a great deal of citation. Shepard's paper for the Indian Ocean, less so, but specific to the Indian Ocean, whereas the Gwinnett paper then includes the coral triangle and a few variables. And then we globalize this threshold concept in the Donner paper in 2005, and then again with Van Hooydonk in 2013. The variability papers, the key paper there is, initial paper in my mind was the Regal and Pillay paper, which looked at some different environmental stresses over large global scales and sort of an anecdotal evaluation of modifying stresses. The East African paper of ours in ecological monographs was looked at more types of temperature variation and showed that that region had distinct temperature clusters, if you like, where each of them might have a different outcome in terms of the future. And this was then either further modified with Mina's paper, where he had 9 variables, and some of them included things like current flow and chlorophyll and other things not typically modeled, and showed them both to be influential and also being able to be modeled on a scale of the Western Indian Ocean. The Cholet and Mumby paper was very Caribbean-centric and showed that, in the Caribbean there are different kinds of environments and things such as upwelling, and these might modify bleaching. And then finally, the most recent influential paper in my mind is a Cacklopaglia and Van Woesik paper, where they use a niche modeling approach, which was, I found, a unique approach to looking at where corals would be distributed, where we're looking at corals at a species level, niche behavior. During this time, the first 50 Reefs assessment portfolio was created, and this used a number of variables, and then the portfolio approach, which is to spread the risk, and I think this was a wise approach. The result was the selection was very heavily selecting for the Coral Triangle, East Africa, the Southern Red Sea, Northern Caribbean, and French Polynesia. It results in weaker representation in Australia, the Indian Ocean, Central Indian Ocean, Southern and Western Caribbean, the Northern Red Sea, Melanesia, and the Eastern and Northern Pacific. So this was useful, but after reading this literature, it was clear to me that it didn't always overlap with some of the other approaches. So there was this concern of mine that these portfolio could be methods dependent and depend heavily on the particular variables, and your approach to modeling could result in that, and that has consequences for the types of sanctuaries that we pick. And if you look at the models in the Bayer et al. Paper, you'll see that it's heavily reliant on the threshold concept. That both past, present, and future degree heating weeks plays a big part in some variability in the degree heating weeks, but it's generally heavily reliant on a threshold concept. There are modifying variables. Cyclones could be affecting recovery rates and as well as connectivity. So there is some contribution from the other axes of the sanctuary. But once again, it is heavily reliant on that threshold idea, and that therefore requires a sort of a critical view of that threshold approach and to what extent it's a reliable predictor of a future state of coral reefs, and what might be the best response curve or response model to degree heating weeks. Is it always a declining cover with cumulative degree heating weeks, or are there some other types of responses? Those are key questions to ask about this approach, where the exposure axis is heavily reliant on a group of related variables. So that's part of our mandate here, is to consider this, and going forward, is there a way to maybe balance this out more in a way that might be less risky? So what I'll do here is sort of take us through a quick tour through some of the empirical results, just to be provocative, essentially, to open our minds to the possibility of different ways of looking at things, and maybe some of the blind spots or biases we might have had in our research, in order that we can think about sanctuaries maybe in the light of good empirical studies. Here's an example of two very different responses to degree heating weeks. One both in the eastern Australia, the GBR and south, where the northern GBR showed quite a strong relationship with degree heating weeks in 2016 and percent bleached corals, and on the right, where in the southern part of the eastern Australia, there was really no relationship, and very weak relationships with the taxa. So it shows you sort of the geographic variability, and the fact that these variables can predict very well in some cases and less so in other cases. When you look at this idea that there are different ways to measure exposure, and that could be the frequency, the duration, and the spatial extent. These things can be interrelated in ways that are sometimes important to distinguish. For example, the Hughes paper argues that the frequency of bleaching events is increasing, but in fact, when you look at the cell level that Skirving did, you find there's really no increase in frequency in particular cells, but there is an increase in duration and spatial extent, such that it was possible. You can interpret the Hughes paper as a case where data is pooled into large areas, and then you can make conclusions about that area, about frequency, but it may actually be that duration and spatial extent are actually the drivers of those patterns. So this is an example where there's spatial dependency on the relationship with these important components of exposure, duration, frequency, and spatial extent. These are some examples of relationships between variables, environmental variables, and either bleaching. And they show quite a bit of variability and many variables involved in the response to thermal stress. The Caribbean paper on the left is often used as evidence for a 4-degree heating week bleaching response and an 8-degree heating week mortality response. And in a gross sense, that may be true, but there's a lot of variability around these points, and even at 0-degree heating weeks, you're getting over 20% of the corals bleaching. So this variability suggests that any sort of distinct thresholds like that have to be considered in the context of this variability. And in the upper right, you'll see some examples of how many variables are influential in bleaching: geography, as well as various forms of variation, as well as threshold concepts, and each of them contributes something to the response, showing that what a complex phenomenon bleaching is, and that phenomenon is even more complex when you look at it at the taxonomic level in the lower left, where we looked at many taxes' responses to many variables in a transect from East Africa to Fiji. You'll find that every taxa seems to have its own kind of response to specific environmental variables, and that makes it very hard to often evaluate things at the coral cover level where many taxa are combined. It also points out the importance of looking at many variables. For example, in this case, we found longitude and ecoregions to be among the strongest variables of bleaching, and mostly ecoregion and longitude haven't been included in previous models. So these missing variables that are not evaluated may be very important, and I'll talk about that later. And specifically on the bottom right, when we pooled our data into ecoregions, you can see that, and there's very different levels of resistance. Here, resistance is a measure of the sensitivity of a coral, i.e. the bleaching, divided by the exposure, and we use two types of exposure: cumulative thermal anomalies and a multivariate one, and both of them show this pattern of very different sensitivity at the ecoregional level. So this sort of undermines the idea that there's a global response to corals, and more would argue for local regional history, possibly evolution within these ecoregions, or exposure. At least one of those things is very influential. These papers as well remind us that the complexity once again. And the paper on the left is a Safé paper where they look at in situ data, looking where data was collected on temperatures every hour to 3 hours. So that's very different from satellite data, which is mostly once a day, nighttime radiation. Here they have hourly data, and sure enough, that daily range of temperature turns out to be one of the strongest predictors of tolerance or resistance to stress. So we could see that the scale of the data that you have temporally and as previously spatially can be quite influential in what you consider a refuge. And the paper up on the right is the Kenyan to Fiji transect. Again, you can see longitude being a very important influence, not to mention coral communities, and other things that are not typically looked at, such as high peak spell and bimodality, turned out to be stronger than the average degree heating weeks. So you can see if we're not including some variables, we may be missing potential impacts and potential disasters in that case. And I think that bottom right for the Central Pacific is, to me, a very interesting case where some unexpected things like nitrogen provide some thermal tolerance, and previous exposure in this area often heavily influenced by El Nino. So for me, these kinds of papers, again, argue for variability as highly influential in bleaching and something we have to consider. Here again, there's another series of provocative findings that argue for context and time and space. The paper on the left evaluated the Indian Ocean sites where we had data on coral cover in many sites. I think it was 1,000 plus sites in the Indian Ocean across the 1998 event. And in this case, there was no relationship with cumulative degree heating weeks or the 1998 peak event. But what we did find was a temporally dependent relationship with the multivariate stress model, the 9-variable model, where there was no relationship prior to the 98 event. Immediately after it, there was that negative relationship we would have predicted. And then 5 years later, it broke down and was considerably weaker. And this had also an effect on the community structure across that event. But it can be that across an event, you can have a response shortly after the event, but it recovers and that pattern disappears. But possibly over more and more subsequent events, the patterns that were seen in the initial disturbance may not replicate themselves over time. And I think that's what we're seeing even with a multivariate stress model, is that as we look at it over time, its predictive ability seems to be getting worse. And so it may have been created for a particular time and space period, but now when applied into the future, you have weaker and weaker models, and weaker model fits to the data. So that's another important thing to think about. In this case, it's not symbiont switching, or it could be, but it could be a whole bunch of things, including community structure, other types of resistant factors, and whatnot. Another thing here that I want to bring to your attention, it's important later on, is these hump-shaped relationships with cumulative degree heating weeks. So you see one in the bottom left in the the East Africa to Fiji transect, where coral cover is actually intermediate at a pretty high cumulative degree heating months, or 30, and declines to either side. So this is provocative because it's against the model that as you accumulate degree heating weeks, coral cover declines. It suggests actually a more modified pattern where either too little or too many degree heating weeks is actually detrimental, but there's sort of a right amount of degree heating weeks. At least that's the way I interpret that. And this is based on 223 sites, I think, on that transect. But even more provocative is Darling's paper, where she uses a completely different data set, which is line transect data, as opposed to the visual observation on the left. And again, you see what is more of a hump shape distribution of the data around the maximum degree heating weeks in 2014. So you may say there's no pattern there, but in my mind it tends to show some sort of distribution around a mean response to about 7 or 8 degree heating weeks, actually having the most coral cover compared to areas either to the left or right of that. And in Australia as well, the largest big study of mortality in corals doesn't really list cumulative degree heating weeks as one of the stronger variables. It's still some of the other issues there, like crown of thorns and storms. And so, in these longer term data sets, there's a lot of additional factors going on. Here, I just wanted to bring in the aspect of life histories, because when Darlene et al. Break down their coral transect data into life histories, you can see some of the variability there. I won't go into the details, but you can have, measurable effects on one life history and not another, depending on what you're looking at. And that would also be the case for the Eastern Indian Ocean study of Zinke, where they found life history and environmental variables often interacted. And that would also be the case for East Africa, where a long-term transect of 20 years displayed patterns that were more in line with a life history response to disturbance than any just particular disturbance to coral cover itself pattern. One of my hypotheses that I think is generated by the empirical data that I've showed is that the relationship between degree heating weeks and coral cover is complex and maybe not what's expected in terms of a declining coral cover with cumulative degree heating weeks, but rather there's a balance between chronic and acute stress, such that areas on the left where there is low exposure to thermal stress and therefore low resistance may result in very deadly anomalies. That was, when they do experience anomalies, they in fact experience high coral mortality, and possibly to the extent at which recovery may not be as high as it potentially could be if corals are wiped out on such a large scale. But when you look at the right side of it, these are areas that are chronically disturbed and probably also acutely disturbed by anomalies, and they also are unable to recover. Even though they may have high resistance, they may be slow growing, stress resistant corals. So there is that possibility that this exposure metric is predicting coral cover, but not quite in the way that's expected from the models, and that has consequences for the types of sanctuaries that we might be proposing. I classified all the sanctuary papers by their type of sanctuaries as avoidance, resistance, and recovery. And what you find is that 97% of the models being used for sanctuaries are currently essentially avoidance sanctuaries, and much less in terms of resistance and recovery. And that may be a problem if the response to degree heating weeks is not that which is expected, but more of this bell-shaped pattern that I'm hypothesizing. So there's a need then, therefore, as I argued in the beginning, to consider resistance and recovery sanctuaries as something that needs to be included in these sanctuaries, because they may offer different attributes that may reduce risk by including these additional axes. I'd like to quickly go through the possibility that what we really require is multiple models and look for where they correspond, because that could in fact be low risk, in the sense that if they're predicted to have low exposure or low and high resistance and fast recovery, that may be the type of locations we're looking for, and they may not overlap, but at least a multi-model approach might more likely identify these areas. So I'll just briefly go through some work I've recently done on comparing two types of models in the Indian Ocean. One is a variability model based on both different environmental backgrounds and different clusters of of environments that you see in the Indian Ocean, but also multiple variables, 17 variables, of which some of them are atypical variables, such as fisheries management, which turns out to be significant. Oxygen, calcite concentrations both turn out to be significant, and skewness and kurtosis, which turn out to be significant in predicting coral cover in the Indian Ocean. And compare that with a threshold type model using mortality from the 2016 bleaching event in the northern Great Barrier Reef. This is what we did is predict coral cover in 2020. That's the black line. And what you can see is the coral cover is predicted to be 35% in 2020. Distributions as seen in the black line. And in 2050, the RCP model, using the threshold model, predicts very high mortality and very low coral cover by 2050, 90% being below 25%. But when you look at the variability model, you can see considerably less coral mortality or more coral cover in those years. And particularly when you include fisheries management, which was one of the significant variables, you get differences that are not particularly different from 2020, particularly in the high-end coral cover areas. If you then compare models, you'll see that they don't fit very well together, but there is overlap, and that overlap tends to be in this cluster 1 and 4 locations that run from eastern Madagascar to the African coastline. And so these might be areas that have been identified by 2 methods and therefore might be high potential sanctuaries. If you use a multivariate stress model, which is this, plus you combine known biodiversity levels, this is sort of the predictions for that area. And you can see across that area from Mauritius to East Africa, you either have some combination of low multivariate stress or high biodiversity. That's what you're seeing there is sort of the balance. So in Mauritius, you tend to have low environmental stress and moderate diversity, so that comes out as a selected location. But as you move towards the African coastline, you have moderate environmental stress but high biodiversity, and those red areas get selected as sanctuary areas. So you can see in these 3 different models, you can get some overlap, and that's hopeful for a way of approaching this. And in this case, we use different variables and different assumptions about them. So my argument is that the current sort of generic global environmental models are really just looking at coral cover, which is a composite metric of many life histories, all within a larger, very large taxonomic group with a great deal of differentiation. And that could be our entry-level model, but in fact, you need to consider the possibility that every environmental cluster out there might have its own model for a particular type of life history or even a taxa, and that's more this niche modeling approach that you can use. And that also there need to be a lot of consideration of more environmental variables. So I'm considering the future may look more like this matrix of possible models rather than a few threshold or even a few variability models for that matter. Some things that I think emerge from this work is that threshold models are among the many relationships of coral stress with bleaching. They're not always deadly. They can be stabilizing effects on coral cover. That's something that hasn't really been thought about well, but I think that's a viable hypothesis. A lot of geographic context in the results, and therefore there is a need for models to contain more of that complexity in space and time. History makes a difference. Where you're exposed to chronic or acute stresses, your responses to acute stresses is going to vary and not always be a threshold level response. There are stabilizing, destabilizing, modifying environmental variables, and these need to be thought about more carefully, and in my opinion, they need to be included. And so the idea is then that we can potentially model sanctuaries for maybe different life histories and for different properties of avoidance, resistance, and recovery. So where are we going with this 50 Reefs 2.0? One of the things that we do have to work on already is the fact that a number of people have put quite a bit of effort into developing environmental exposure and model sanctuary locations. They differ sometimes in terms of the spatial scale at which they identify them. Sometimes they're simple GPS points, sometimes they're larger polygons in the sea, other times they're blended cells next to one another. But there is a basis for evaluating sanctuary with existing information already. And from that, we might be able to identify different types of models, ones that are driven mostly by thresholds and therefore avoidance locations, maybe other models that are a little bit more driven by multiple variability and modifying variables, and then may have more resistance and recovery aspects to them. So there is that potential to use existing information to help develop this second tier process that we're going through now. This is an example of what we've done. We have combined all of these models into a GIS program, which then can allow you to evaluate and look at where they're located, acknowledging that some of them are very local scale and others are global scale. But that creates the potential for understanding these models and perhaps identifying overlaps and possible places of conflict or possible models that are different from one another based on the type of avoidance, resistance, or recovery that they represent. So going forward, I think this paper sort of represents the kind of thing we're talking about, which is sort of modeling coral cover in the coral triangle with very large data sets contributed by many NGOs, and using big environmental databases such as BioOracle. In their case, they did not include some other very important variables I would have included, including the NOAA data and metrics you can calculate from that. But it's a very good example of where you can identify high coral cover areas and then use Mark-Sent sort of mechanisms to propose priority areas. Can we do this? I think we can. I mean, there is big data out there. Various people have compiled data. People are generally willing to share data as long as the appropriate mechanisms are in place. So I think the benthic data, the environmental data is there. It's just a matter of really coordinating it and maybe taking it from the existing 34 site papers to a new set of models that might have the lessons learned from the previous work into developing a more refined set of models. Conclusions from this particular part of the study is that that we believe there are three types of sanctuaries, and each of them represents a different aspect of the environment: the physical chemical environment, the biological environment, and the ecological environment. Do they overlap in space? That may be something we can test with already existing models, or something to test moving forward. We have emphasized exposure sanctuaries, and yet we haven't tested very well, in my opinion, the consequences of these exposure models on coral cover. And in many cases, as I argued, that the responses may not be the expected declining coral cover with increasing cumulative exposure, but that it exists within a chronic and acute framework where the responses depend on the historical exposure and then the adaptive capacity or resistance of the organisms that are being exposed to chronic and acute stress. there may be areas that we're overestimating that sensitivity because we haven't considered sensitivity very well. And I think many reefs in the coral triangle may represent reefs that are more tolerant than is fully appreciated. We're not looking at all the variables. Some of the modeling approaches have been a very confined approach with limiting variables, and yet then we often find surprises when we look at more variables. So this kind of exploration of more variables seems to be something we need to continue. There's a likely that regionalization at some scale is going to be needed to make accurate models. What that scale is and what the attributes are is important. Is it a shared evolutionary history? Is it a shared physical environment? Is it some shared ecological interactions? It's very possible that every province may need its own model, or every ecoregion, or possibly there are different SST cluster groups, and this needs some further thought. And in general, I believe that the future predictions are currently fairly dire, and they may not be as dire as the data suggests, because there are different types of sanctuaries, and the responses are changing over time. There is acclimation adaptation processes underway that could significantly modify the current models that don't evaluate that diversity in great detail. I just want to conclude by acknowledging that we haven't talked about the social context of this portfolio, but that is something that we as NGOs are working on, and we consider it extremely important. It may very well limit the locations that we can work in, and the type of policies framework, the type of governance in place are things that we have to consider. In many areas, for instance, in a refugee area in southern Kenya, northern Tanzania, we've seen the willingness of people to engage in restrictions depends on their evaluation of the strength of their governance. Some areas have strong governance and they tend to be in favor of MPAs and other types of restrictions, but areas with weak governance, they don't see the point. And that's something we have to consider going forward. We can look at governance institutions and which are weak and which are strong, and potentially build those weak institutions in areas that we think are high priorities. And these types of things are possible. This middle graph here shows a case of different communities and their strengths and weaknesses. And you can see there is generally some groups in the red that represent people with strong institutions, and others where specific institutions are weak. And those can be addressed through social capacity building. And then on the right, we can look at larger scale kind of metrics of success of MPAs, collaborations between countries and recovery times. And you can sort of map out what might be areas where there's high potential for engagement and the type of engagement you might need. Is it engagement to promote recovery of fish, or is it engagement to increase the capacity to manage MPAs? These things are possible and they're ongoing, and we won't forget them. But I just wanted to mention them just in case it was not clear that we also consider this aspect of the problem important. So I leave you with some questions, and these just form the basis for the discussion that we'll have next week. And if you feel obliged or interested in maybe responding in writing to any of these, you can. Or if you think that this work has created a new set of questions that I'm not addressing here, feel free to write those down, and you'll be given some chance to express your opinions about this particular presentation, some of the proposed ways forward, and then maybe help us resolve some of these questions, maybe identify what are really important versus which are just sort of rhetorical questions in order to move this program forward. So I'll leave you with these questions just for a few seconds to read, and otherwise I look forward to talking to you shortly.